Welcome to the SAFECode e-learning course Introduction to Cryptography. The primary targets for this course are software developers and software designers, but architects and test engineers may also benefit from its content. The goal of this course is to provide an insight into the correct use of cryptography in applications. Additionally, it will give an overview and an understanding of the most important cryptographic concepts. When you have finished this course, you'll be able to choose the right cryptographic algorithms for your needs, and you'll be able to decide whether a symmetric or an asymmetric cipher fits better for your use case. This course will show the differences between encryption and hashing, and you'll be able to determine the correct uses of encryption, hashing, or both. Finally, this course will detail the common practical pitfalls to avoid when applying cryptography in applications. Our agenda starts with an overview of cryptography and continues with an explanation of hash functions. We'll describe the differences and the correct uses of symmetric and asymmetric encryption techniques. Next, we will discuss the concept of random numbers and its significance in cryptographic algorithms. Additionally, we'll show some examples of cryptography in action. We will also talk about practical issues, the difficulty of building cryptography that works correctly, and the importance of using existing established and accepted cryptography toolkits instead of developing them on your own. Along the way, we will look at some cryptographic code samples and their correct use on various platforms. And finally, we will summarize the most important points we've made in this course about cryptography. Let's discover the world of cryptography now, starting with an overview of its concepts, the types of problems cryptography tries to solve, and some fundamentals. Unfortunately, cryptography is one of those subjects that's too often misunderstood by designers and developers. Some appear to believe that just by using crypto, their applications will be magically made secure. Some think they don't have any data that is sensitive enough to be a secret, and so they have no use for crypto. Others believe they are great designers of software, and therefore they must also be great designers of crypto protocols and systems. Some fail to see that cryptology is a constantly evolving subject, and as hardware and software progress and new attacks against crypto systems are discovered, one's choice of crypto use must also evolve with time. Others suggest that just basic crypto is enough, believing that their adversaries lack the knowledge or resources to attack strong crypto. That, too, is an assumption that has been proven wrong many times, as justifying an attack effort merely depends on how interesting to the attackers the protected information is. Traditionally, cryptography's uses are associated with secrecy and confidentiality. If you don't want somebody to know specific information you are using, then you would turn to cryptography to hide it. This should be possible both for information stored on a system and for information transmitted over networks. Cryptography can provide other services as well. When we protect the secret nature of communications, cryptography can also help with integrity, proving that a message was not tampered with while in transit. What the recipient received is exactly what the sender produced. Any change would be detected. Cryptography can also be used for authentication. Parties in a dialogue are able to prove that they are indeed who they claim they are. Another use of cryptography in day-to-day communications is in digital signatures, where it is shown that the declared sender actually sent the message in question, with the added advantage of non-repudiation. That is, at a later date, the sender cannot deny that he or she has, indeed, sent the message. Repudiation is a term borrowed from the legal world. Once a contract is signed, there must be mechanisms to prove that the signing party actually did sign it. Other uses of digital signatures would be, for example, code signing and signing of digital documents. Even with its many uses, there are some problems that cryptography alone cannot solve. An encrypted channel does not guarantee a secure channel. How would you transfer, manage, and store the keys needed for setting up the encryption? Does your key exchange protocol leak any sensitive information? Even when applying cryptography to a communication channel, it might not be secure. A side channel could leak information that can be used by an attacker to retrieve sensitive information of the communication. For example, a side channel attack measuring the time it takes for an encrypted message to get processed might be used to estimate how long the used passphrase is. Besides side channel attacks, key exchange and key management man-in-the-middle attacks must be considered. Perhaps there is a snooping third party in the middle of your conversation, posing as the other party. Code that has been signed has no guarantee that it's also secure. Remember, Any design or coding implementation errors would still be present despite a signature. If an attacker maliciously modified the source code before it got compiled and signed, you would get a malicious binary passing all signature checks. Also remember that you have to take care of crypto keys on the organizational side. Signing keys can be lost, or professional attackers may even consider legitimately buying a certificate, enabling attackers to sign their malware and make it look trustworthy. Even well-known libraries providing crypto services are not immune to the occasional error in coding. And you're not immune to mistakes in initialization or choices of ciphers that might downgrade the security offered by them. Attention should therefore also be paid to integrating crypto libraries and APIs correctly. At the end of the day, cryptography should be understood as being one more tool in your toolbox for assuring security. It is not a magic bullet. Now that we have established some background, let's move on to hashing. When you consider the fingerprint of a person, you're reducing the identifying characteristics of the person to a single set of values. It is almost certain that there aren't two people in the whole world who present the same fingerprint, and we can therefore use fingerprints to identify and distinguish people with a low margin of error. Hashing provides the same functionality as fingerprints, but for files or any kind of digital content. By passing the stream of bits that makes up that content through a hashing function, we're able to create a fixed-length output string unique for that stream. That is the hash, and it works like a fingerprint. There are 3 requirements for an appropriate cryptographic hashing function. It must be collision-resistant, meaning that it is not feasible to find 2 inputs that produce the same hash. It must be infeasible to change the message without also changing the hash. Ideally, just a small change to the input has a vast effect on the created hash. It must be strictly one way, meaning that it is not feasible to find an input that would create a given hash. Since a hash is unique to a given input, it can be used to verify its integrity. Send the input via one channel and the hash via another. Then recalculate the hash of the received input. And if it matches with the original hash, the received input matches the original. While very useful for verification purposes, hashes are not enough to guarantee confidentiality. Since the hashing function is one way only, you cannot recover the original input from a given hash. They also provide no authentication, since anyone can hash any input. There's no guarantee in the hashing process that any single person was responsible for the hashing, which we would need for authentication. That also implies that hashes on their own cannot be used as digital signatures, as there is no needed secret involved in creating a hash. There are some well-known hashing algorithms that are commonly encountered in software. The ones marked in red should not be used unless they are necessary for backwards compatibility. MD5 and SHA-1 have been shown to contain weaknesses that make them vulnerable to collision attacks. For MD5 in particular, an attacker can easily obtain 2 different inputs that result in the same hash. No SHA-1 collisions are yet known publicly, but we expect them soon as crypto attacks and computing power advance. Today, you are advised to use the SHA-2 family of hashing functions when implementing new applications that provide integrity checking. No practical attacks in the SHA-2 family are known, but we point out that SHA-2 using a hash length of 224 bytes is considered too short for security purposes, and its use should be discouraged. Longer hash lengths are highly recommended. The National Institute of Standards and Technology has proposed a new standard hashing function called SHA-3, based on an algorithm known as Keccak. Since it's a different type of algorithm compared to the previous SHA families, it's reasonable to think that it will not be open to the same weaknesses that might target SHA-1 and SHA-2. We recommend using SHA-3, but please keep in mind that due to the newness of the algorithm, it's not yet very widely known. When doing hashing, the usual workflow is to initialize a hashing engine, update it with the content to be hashed, and receive the hash at the end. You'll see this in most open SSL operations, for example. Here we illustrate it with a SHA-512 hash of the content of the string contained in the plaintext variable in Java. The hash is available as an array of bytes at the end. Please note that you can call the mupdate function as many times as you need to. We'll just pause for a moment here so that you can look through the code samples on the slide. Let's go on to talk about symmetric encryption. The symmetric in symmetric encryption refers to both sides of a dialogue having exactly the same key with which to encrypt and decrypt messages. The key is used by both parties in the same way. It is applied together with the text to be encrypted, which we call plain text, to an encryption function, and the result is the encrypted text, the ciphertext. For decryption, the ciphertext and the exact same key are applied to the decryption function, and the result is the plain text. One of the immediate problems with symmetric encryption is that since both sides of the dialogue share the same key, it is impossible to say who has originated a given message. Non-repudiation is not possible when using shared keys. Like other forms of reliable encryption, symmetric encryption's first use is for confidentiality in communications, as only parties who know the shared key will be able to decrypt and encrypt messages. One important characteristic of symmetric encryption is that it's generally faster than other forms of encryption. Although with the latest advances in off-the-shelf hardware, this point has become less critical. It's still important to point out that in volume, messages will be handled faster by symmetric encryption. Please note that using symmetric encryption does not protect against tampering with transferred data. One of the most difficult aspects of symmetric encryption is the handling of keys. If only 2 people are communicating, 1 key will suffice. However, if 10 people want to communicate, they will need 45 keys. And if the number of people is 100, the number of keys needed will be as many as 4,950. These keys will also need to be distributed in a secure, out-of-band way so as not to be intercepted. As you can imagine, it's very difficult to scale up to the large numbers of participants without either weakening the scheme or investing a big effort in it. Diffie-Hellman is a method for securely exchanging symmetric keys without transmitting the actual key. Take care, however. It does not provide authentication and is therefore susceptible to man-in-the-middle attacks. When talking about symmetric encryption, it's important to discuss the 2 ways it is implemented, as stream cipher or block cipher. A stream cipher encrypts 1 bit at a time by XORing it with a stream of data that is produced by an internal mechanism using the key and pseudo-randomly generated data. The changing states of this internal mechanism lend to stream ciphers the alternative name of state cipher. Block ciphers, by comparison, operate on fixed-length sequences of bits called blocks and transform those blocks by using the encryption key and a sequence of permutations and substitutions on the original text. To allow block ciphers to also work with input larger than the block size, so-called cipher modes of operations are applied. There are too many cipher modes of operations to cover here. However, we caution you about the weakness of electronic codebook, or ECB, in hiding patterns of data. On the other hand, the exceptional throughput provided by the Galois counter mode, known as GCM, is worth mentioning. Let's have a more detailed look at the ECB and the GCM/CBC modes of operation. To illustrate some of the differences between modes of operations, we can demonstrate how ECB, electronic codebook, compares to other modes such as CBC, cipher block chaining, or GCM, Galois/counter mode. From the picture, we can see how the mode of operation chosen influences the quality of the encrypted result. The ECB mode shows leakage of information that may substantially amplify the chances of recovering meaningful information from the ciphertext. It is crucial to choose a suitable mode of operation for the application with respect to performance and security requirements. GCM, Galois/counter mode, is the mode of operation currently recommended in the crypto community. Many of the modes of operation require an initialization vector, or IV, as input along with a secret key and the plain text. The mechanism of generating the initialization vector is central to the effectiveness and security of the cipher algorithm. The initialization vector is not secret and is transmitted along with the ciphertext. Due to the fact that a plain text encrypted with a symmetric key will always result in the same ciphertext, it's important to set up the initialization vectors properly. The IV will be used to generate different ciphertexts if an identical message gets encrypted with the same symmetric key. Therefore, you should always use a cryptographically strong random IV as required by the applied mode of operation. Now, let's look at some examples of symmetric key algorithms. RC4 is an example of a stream cipher. It's very fast but has a number of severe weaknesses in many of its applications. For example, if you search the web, it's easy to find reports of the weaknesses present in the wired equivalent privacy, known as WEP encryption algorithm. Also, RC4 itself is showing more and more weaknesses and should not be used in modern applications. Data Encryption Standard, or DES, which for a long time was the standard crypto algorithm used by the U.S. government and the software industry, is a block cipher that's considered completely insecure by today's standards. Note that since the Electronic Frontier Foundation introduced a DES brute force cracking machine, known as EFF DES Cracker, in the late 90s, DES became officially broken. 3DES, also known as triple DES, and AES, the latest block cipher certified by the NIST, are the successors to DES. AES is the currently recommended symmetric cipher. Other examples of popular symmetric algorithms are Blowfish and Twofish. The crypto community currently considers AES to be the stronger alternative to these two algorithms. Remember, a weak initialization vector or the wrong choice of mode of operation can weaken even the strongest algorithms. This brings us to asymmetric encryption. In contrast to symmetric encryption, asymmetric encryption offers a solution to the complex problem of key management. In 1976, Diffie and Hellman published the first paper about public key cryptography, also called asymmetric key cryptography. In their scheme, two keys are used instead of one, but they have mathematical properties that bind them together in a particular way. The two keys are generated together. One is called a public key and the other a private key. They are the result of a mathematical process built so that the knowledge of one key does not permit, in a feasible way, the derivation of the other one. As a result, one of the keys, called the public key, can be freely distributed, while the other, the private key, is held secret and well guarded. The two keys together are referred to as a key pair. The keys are applied in different ways for signing and encryption, as shown on the next two slides. Alice should be the only party with access to Alice's private key. If Bob would like to send an encrypted message to Alice, he can encrypt the data with Alice's public key. In that case, only Alice would be able to decrypt Bob's response. However, Alice would have no guarantee as to who sent her this confidential message, only that it was encrypted using her own public key. Because of the differences in encryption time of asymmetric and symmetric encryption, asymmetric encryption should not be used to encrypt large amounts of data. Instead, common practice is to use a hybrid approach, which is to generate a strong symmetric key and encrypt the data using symmetric encryption. Then use asymmetric encryption to encrypt/decrypt the symmetric key. If Alice wants to sign a message, she'll use her own private key. As you've already learned, asymmetric crypto is not very fast. Therefore, the whole message is usually not signed, but just a hash of the message. When Bob receives the message together with the signed hash, he's able to test whether this message was modified and if it was actually signed with Alice's private key. First, he decrypts the received signature with Alice's public key, resulting in the original hash value. Second, he calculates the hash himself from the received message. If both hashes match, the authenticity and integrity have been verified. However, how does Bob know that the public key he used to verify the signature is really Alice's? The assurance is usually achieved by means of a so-called public key infrastructure, or PKI. To establish a public key infrastructure, a trusted third party, also known as a certificate authority, is required. The certificate authority validates the identity of the private key owner. The CA signs the public key of the applicant and sends back the signed public key as a certificate to the requestor. Another task of a certificate authority is to verify the validation of issued certificates. In our example, Alice is generating her private and public keys, and she sends her public key to the CA. The CA signs the public key and sends back the public certificate. Alice signs her message with her private key, and anybody else is able to check the signature with Alice's public key, which is not a secret. The certificate has been signed by a trusted CA, and its validity can be verified through asking the CA. The de facto standard for asymmetric crypto is Rivest-Shamir-Edelman, which is known as RSA. It can be used both for encryption and signing. Currently, the recommended minimum key length for RSA is 2048 bits. Digital Signature Algorithm, DSA, only provides signing facilities and no confidentiality. During setup, it should offer a choice of hashing algorithms to use. Make sure you opt for the longer forms of SHA-2 and not the default SHA-1, and key length of at least 3072 bits. Like all crypto systems, DSA requires a high-quality source of random numbers in order to be secure. Here's an example of the use of RSA encryption on C#. You're probably recognizing a pattern. Initialize the engine, provide the setup information and the content to be transformed, encrypted or hashed, and receive the result. This example follows the same flow. System Security Cryptography is provided by the Microsoft library mscorelib.dll, which also provides, among others, AES, Diffie-Hellman, DSA, HMAC, and SHA-1 and SHA-2 facilities. We initialize a service provider, giving it the necessary setup information. In the case of RSA, it is an RSA parameter structure, which contains the internally used exponents, primes, the coefficient, and the modulus that RSA needs. Basically, a breakup of the private and public keys. The interesting thing to point out here is that the fields containing the private information are not serializable. That doesn't stop a user from getting the values and exposing them somehow, but it shows how the library helps the protection of sensitive values. We pause briefly here so that you can look at the sample code on the slide. Let's move on now to the next important element of crypto, generating random numbers. Many cryptographic protocols require strong random numbers. Computers are not good random number generators. The best an algorithm can do without specific hardware is to generate a stream of pseudo-random numbers. This is because the algorithms used for number generation are deterministic and depend on an internal state initialized by a seed in order to generate pseudo-random numbers. Using a good pseudo-random number generator is key to good crypto. Each platform or programming language has implemented pseudo-random number generators, such as devrandom and devurandom on Linux, bcryptgenrandom or rands on Windows, and securerandom in Java. On Linux systems, there are two system sources used to generate pseudo-random numbers, devrandom and devurandom. The difference between them is that devrandom uses real entropy sources like keyboard input or mouse movement to generate a high-quality random stream, as long as there's enough real entropy available. Its counterpart is devurandom, which will not block, unlike devrandom, which will stop producing output if not enough entropy is available. It gives results with less entropy than devrandom, because it is based on a pseudo-random number generation algorithm. Now let's look at some code examples of using random number generators on different platforms, starting with Linux. In order to obtain a random value on a Linux system or similar that provides the devrandom and devurandom facilities, read the length of necessary bytes from the device and cast it into the necessary type. The POSIX RAND family of functions is not adequate to use in the absence of devrandom facilities. In that case, you'll need to provide an acceptable solution for your environment. Let's pause a moment for you to review the sample code on the slide. On Windows, bcryptgenrandom is a function in the Cryptography API, Next Generation, or CNG, used to generate cryptographic secure pseudo-random numbers based on a series of entropy sources like process and thread ID, performance counters, CPU counters, and a hash of the user environment. CNG is available in Windows Vista and Windows Server 2008 and later. The CNG API should be used where it is possible. It's recommended that you use CNG rather than Microsoft Crypto API, known as CAPI. If you need to support earlier versions of Windows, you can use the CAPI, but be sure to use the cryptgenrandom function for random number generation, or the rands method. Remember that if you do not want to incur the cost of including the Crypto API in your program, You can make use of RAND-S, which is part of the C runtime or CRT libraries. We'll take a moment here so that you can look at the sample code. In Java, the best way to generate a secure random number is to use the secure random class. Depending on the platform and implementation, the random number might be produced from a pseudo-random number generator or a PRNG, which means that a deterministic algorithm is used to produce a pseudo-random sequence from a true random seed. Other implementations may produce true random numbers, and yet others may use a combination of both techniques. The random number generator seeds itself on first use when calling secure random next bytes. Now that we've talked about what cryptography is about, what its major elements are, and how cryptography is done, let's see cryptography in action. Here, we will look at two of the most common crypto usage cases found in the field. TLS, including its predecessor SSL, now considered insecure, and digital signatures. When commercial use of the Internet emerged, cryptographic protocols had to be developed on top of the existing ones to permit secure financial transactions without requiring a big overhaul of the existing infrastructure. One of the best examples is the use of TLS in order to secure web transactions. In the most common use of TLS, the server offers authentication to the client. You are able to recognize that by the lock icon in your browser, commonly placed near the web address that appears when you connect to a site using HTTPS, which means HTTP secure. Here, the server sends its verifiable certificate to the browser client. This protects the client from connecting to a malicious spoofed server and from man-in-the-middle attacks, where the communication might get intercepted. In order to enable this function, modern browsers carry lists of so-called Trusted Certificate Authorities, or CAs. Those CAs are the ones from which web server operators may request a digital certificate to protect the HTTPS communication of their web server. When the browser connects to an HTTPS web server, it will analyze which CA issued the TLS certificate the web server presents. If this certificate was issued by a CA that is marked as trusted in the browser, the connection will know that it is indeed the legitimate web server and will establish a secure connection. Otherwise, a warning will be presented indicating a certificate error. The TLS protocol is built using the previously discussed cryptographic services of random numbers, asymmetric encryption, symmetric encryption, and hashes for message authentication. The process of generating and establishing the secure TLS communication channel is known as the TLS handshake. TLS is only as strong as the set of ciphers it's configured to use. As a first step in securing a TLS system, one should disable the null cipher and all other ciphers supported but considered weak at the time of implementation and deployment. TLS also has been recently found to be susceptible to a number of attack vectors. For example, the Beast, browser exploit against SSL/TLS. Crime, compression ratio info leak made easy. Freak, factoring RSA export keys. And Poodle, padding Oracle on downgraded legacy encryption, are well known and publicized. SSL in all of its forms is currently considered broken. TLS version 1.2 or later should be used. The selection of cipher suites is a complex and evolving topic in itself. The Internet Engineering Task Force document, RFC 7525, called Recommendations for Secure Use of Transport Layer Security and Datagram Transport Layer Security, may be used as a reference to help decide on cipher suites and algorithms in a software system. Digital signatures are also very common use cases of applied cryptography. A digital signature is a mechanism for demonstrating the authenticity of a message or document. The building blocks of digital signatures have been discussed already. Hashing and asymmetric crypto are the main elements here. A valid digital signature gives a recipient reason to believe that the message was created by a known sender, such that the sender cannot deny having sent the message, and that the message was not modified in transit. Besides its use in transmission, digital signatures are commonly applied for software distribution, financial transactions, and in other cases where it is important to detect forgery or tampering. Digital signatures are created during code signing procedures to ensure that each software package is legitimate and came unmodified from a specific vendor before being installed on a client machine. As with every solution to a problem, there are some pitfalls. Let's review some practical issues that you'll likely run into when integrating crypto. There are some good choices available when you're looking for good crypto toolkits to use on your development platform. For a Swiss Army knife crypto approach that offers multi-platform support, you should consider OpenSSL. The OpenSSL library and its command line utilities can cover many of the necessary elements for handling different crypto tasks. It has been publicly tested for a long time and is also updated when security issues are discovered. It offers a wide selection of algorithms, modes of operation and key sizes, configuration options, and even a FIPS option. It can be used from the command line, but it also offers a rich set of APIs for application integration. When developing for Java, the Java Foundation classes offer good coverage of the cryptographic basics. Make sure you read the documentation to avoid any initialization issues. For Windows Vista and Windows Server 2008 and later, the standard is to use the CNG, which stands for Cryptography API, Next Generation Library. If you need to support versions of Windows earlier than this, you can use the Microsoft Crypto API, also called CAPI, a subset of the Win32 API. The CNG and CAPI libraries also include the Data Protection API, or DPAPI, which is a simplified encryption/decryption mechanism, where a key or certificate is generated and protected by the Windows operating system. One disadvantage of the DPAPI is that it doesn't work in kernel mode, but only in user applications. The AuthentiCode functions for supporting code signing purposes are also provided by CNG and CAPI. When developing .NET applications, the framework's functions wrap much of CNG and CAPI. Interoperability is an important consideration when integrating cryptographic functions. As we mentioned in the secure random example, the same library can present distinct behavior on different systems. In this case, it is the default PRNG that changes. Keep this in mind when making a decision on which crypto library to use. Prototype the functionality in a snippet of code on the different platforms, and ensure that the cryptographic outputs on each platform are what you expect. We've also raised the point that the list of acceptable crypto schemes keeps changing, according to advances in attacks against crypto and increases in computing power. To illustrate the point, let's recall that DES used to be considered really strong some decades ago, and now it is considered completely broken. Now we advise that you use AES. If you had hard-coded DES all over your work, you would have to manually change all of that code to use AES. The same might happen with AES one day. For this reason, you must be able to change your chosen crypto scheme on the fly, and ideally, give the end user a way to change that choice. Applications utilizing crypto, such as web servers, provide dedicated crypto configuration options to deny the use of null and weak ciphers. The possibility that your keys, certificates, and secrets may become exposed, such as through a security breach, also has to be taken into consideration. For that reason, you should create methods that allow you to rekey, that is, to change anything that is used as a crypto key in your application, without losing data. Even if keys are not exposed, it's a good idea to periodically rotate keys to reduce the possibility and effects of exposure. Depending on the type of secret you use, certificates or shared secrets, the exposure of your secret becomes more likely over time if you're not able to rekey frequently. Also remember that certain cryptographic elements, such as keys and certificates, may have a validity expiration date and therefore will require replacement at some time. And remember, never hard code keys and secret values, as they will be uncovered at some point and be very difficult to remove without significant software update and deployment effort. In the previous slide, we discussed provisions for the case of key exposure. But how to efficiently protect these keys is a complex, real-world problem. The value of authentication based on crypto is based on the assumption that only one user has access to his or her private personal keys. A password written on a sticky note that is easily visible violates this principle, negating the secret factor for authentication. An insecurely stored password or key inside a system does the same. Most often, the secret key or password material will be stored in a file under protection provided by the regular operating system access control mechanisms. This is exactly how private certificates are stored on Unix operating systems, for example, as files in the file system with proper access controls. The Microsoft Data Protection API, or DPAPI, offers some system value and registry-based secure storage facilities based on the user's login information, thereby helping to protect sensitive information outside of the file system's regular access control. Some physical mechanisms include the storage of keys on media, like a mountable USB key or read-only CD that are removed from the system once the key information is initialized, but that might still leave the key exposed to attacks in memory, depending on implementation. A number of well-designed key storage mechanisms are already out there. Those key storage mechanisms should be used instead of rebuilt. Besides key storage, the problem of key distribution is also important to consider. In some cases, out-of-band mechanisms, such as hand delivery, might be the right choice. In such cases, keys must be verified by comparing hashes to detect forgery. Public key certificates are another option designed to distribute keys. If the certificate authority root certificate is distributed out of band in a verifiable manner, other certificates derived from it can be automatically accepted. Let's take a look at an example of using the DPAPI facilities for quick encryption. The incoming data in content is encrypted to data out via the crypt_protect data call. Notice how no password is mentioned. The framework makes use of the user's login credentials and some information about the host used to do the encryption. A flag can make the encryption associated with the current host instead of the individual user, so that as long as the decryption happens on the same machine, the content is recoverable. Please take a moment to read through this code. Cryptography is also used to securely store passwords. Once we decide where to store a password, key, or other sensitive material, we should take precautions so that even if the storage is compromised, it will still be difficult to recover the material. For this reason, you should never, ever save it in clear text or trust outside controls to keep it protected. Make use of all available operating system access controls to protect the storage medium. Once the protected content is accessed, try to minimize the time in which the clear text format is available in memory to keep from having it appear in swap files, core dumps, or debug files. When hashing a password or key, make sure to apply a salt, a random string that protects the hash against rainbow table attacks, where an attacker compares the hash to a pre-computed table of strings and their hashes in search of the clear text that corresponds to the hash. Protect the salt as well as the hash itself, and apply a different salt to every plain text. Another way to make it difficult for an attacker to guess a hashed password or key is to stretch the hash. We use the initial password, its hash, and a salt to feed a key derivation function like bcrypt, scrypt, and pbkdf2, a given number of rounds. These functions are deliberately designed to take a long time and/or a large amount of memory, making it more difficult and time-consuming for an attacker to perform the operations needed to compare hashes. Be sure to pass stronger hashing functions as parameters for key derivation functions. For example, do stay away from passing MD5 as a hashing function parameter, and use large numbers of iterations, in hundreds of thousands or even in millions, as attacker hardware is rapidly gaining capabilities for password cracking. Using high iteration counts is not always feasible, though. For example, imagine you're implementing password-based authentication on a very popular social networking site, where you might have millions of people logging into their portals on your system every second. Because of the key derivation function's high resource demands, you might not be able to handle doing high iteration counts at such volumes on your back-end servers. It's a common mistake to encrypt a password instead of correctly hashing it. An encrypted password depends on a key that has to be stored somewhere, And then the question arises, how to protect the key? On the other hand, when the password is hashed, there's no key, and it's impossible to recover the clear text password even if the system gets compromised. Here are some additional factors to consider. Do not try to build your own crypto solution. Give preference to well-tested schemes that were developed and tested by cryptologists, cryptographers, and crypto analysts. It's very difficult to get all the proper requirements in line, and it's very easy to bungle some minor detail that can weaken even the best designed algorithm. The use of keys and certificates, and in fact crypto in general, is built on a network of trust, parts that need to be kept protected and hard to reach, and your system will inherit this trust and rely on it. Invest time in a proper threat model analysis that examines the what-ifs of any part of this trust network being breached, keys and sensitive material being exposed, etc. Then, design for the worst case. Whatever library or toolkit you decide on using, be prepared to handle the future changes that most likely will take place in that particular crypto solution, be they in algorithms, key lengths, and even library patches. Assign someone in your team to keep apprised of changes that need to be translated to your product, released as patches, or sent as an alert to end users. Here are the takeaway lessons that we would really like to drive home. Crypto is not a magic bullet. It's just another set of tools. Don't think that it solves all of your security problems. It doesn't. Don't try to build your own. Trust established solutions, and if possible, always consult crypto experts. Take your time to find the correct library or toolkit to use. There are many, and some will be more suitable for you in the long run. Then, take more time to make sure you are using the crypto solution correctly. Recall all the interoperability, real-world complexity, and other factors we discussed earlier. Finally, remember that it's all about trust. Your crypto scheme will only be as strong as the protection you put on top of it and the sensitive material it needs in order to work. Here we list a few links and resources that you might want to explore in order to further your understanding of cryptography, its applications, and how to use it correctly. Thank you for taking this course.